Hello everybody, I hope you're having a wonderful vacation so far. Here's your video on improper integrals. This is the main goal for you to learn this vacation, how to do improper integrals, how to recognize them, and how to deal with the three main types of cases for an improper integral. So this topic is a bit broad because again there are three cases, and within the three cases there are several different types of examples you need to be able to deal with. The more difficult types, which do come up on the AP exam, also involve integration by parts, partial fractions, U substitution, L'Hopital's rule. It kind of combines everything. So they can be a bit intense to do, but we're going to start off with the introductory level ones as always and slowly work our way up. Improper integrals, let's see. Basically, they're integrals that involve infinity in some way or another. So one way that they could involve infinity is if one or both of the limits of integration are actually infinity or negative infinity. So you might be looking at this and thinking, well, if an integral is really an area under a curve, so let's think about this here. How could I have some function start at 4 and then go on forever? Because this really means the area from 4 to forever. It keeps going. How can an unbounded region have a finite area? And we're going to talk about the different cases. Sometimes it will be finite, sometimes it won't be. Sometimes it will be an infinite area. Because this really means, the reason it's called improper is because this thing just keeps going and going and going. And it really depends on how quickly the function decreases and approaches 0. That will determine whether the area is finite or infinite. Another way that an integral can be improper is if there is an infinite discontinuity within the integral. That mainly occurs if we have a vertical asymptote within the area or within the region that we're looking at. So let's say I have this rational function here. 1 over x has a vertical asymptote at x equals 1 because 1 makes the denominator 0. So I drew that right here. And this is saying, okay, find the area from -2 to 4 under the curve. So if I just keep going and going and going, this is never going to stop going down. And I'm ending at 4. It's also never really going to stop as I approach it from the right. So in this case, what you're going to have to do is break up the integral into 2. And we'll practice a couple of those. Some cases it will be bounded, some cases it will not be bounded. The last case is if there is an infinite discontinuity at one of the limits of integration. So what that means is this looks harmless. It's like, oh, there's not an infinity anywhere in sight. But if you draw it, this function has a vertical asymptote at x equals 0, right here. So this is saying, all right, start at 0 and go to 1. Well, there's no problem with 1. I can think of the area under the curve. But then as I approach 0, it's like, oh boy, this keeps going and going and going and going. How can I find the area under the curve if it keeps going forever? So that's a third type of an improper integral. Take these notes down here, and then we'll actually get to work with some examples. Method. Once again, limits to the rescue. We can't literally have infinity as one of our limits of integration because infinity is an idea, not an actual number. So what we do is we're going to use limits. We're going to use a different constant here, or a variable really. We'll put a variable up here and then let that variable go to infinity. So just like with secant to tangent lines, Riemann sums to exact area, many little pieces to the exact length of a curve, these all use limits. This is another case where limits allow us to find an improper integral. When you do an improper integral, one of two things is always going to happen. Either you're going to find that the limit exists and it's an actual number, then we say that the integral, or the area under the curve, converges, and the value of the integral is whatever the limit was. So whatever the limit is, that's the area under the curve. Another thing that happens is sometimes the limit won't exist. That's going to be going to infinity or negative infinity. Then we say the integral diverges, and the improper integral has no value, it doesn't exist. You can't say that the area under the curve is anything. It's infinite. And this is what I was saying before. We're going to mix in a ton of our techniques that we used before. They're all coming back. I know you guys have missed integration by parts. We haven't done it for a while, and partial fractions, so our old friends are coming back. Another thing to keep in mind here is these words converging and diverging. These are going to be huge words for us the next couple months as we discuss series. Improper integrals are a precursor to series, because we're going to actually use improper integrals when we talk about series and convergence. So we're like in the last main part of BC, and it's all about series, and this is leading us right into it. All right, so let's talk about this topic. Make sure you have all these notes down, pause if needed. Let's talk about this question here. This is usually how improper integrals are introduced. Let's take this function 1 over x, which is right here. We have vertical asymptotes at 0 and 0 respectively. We're going to start at 1, and we're going to go all the way to infinity. So what we're really looking for is the area under the curve from here all the way going to the right. So we're going to keep going and going and going and going here. And we're going to see if this limit exists, and if it does, then I have a finite area. So the thing is, I can't actually do this antiderivative and plug in infinity, because we can't do that. Infinity is not an actual number. So what we're going to do is, instead of doing the limit, or I'm sorry, the integral from 1 to infinity, we're going to do the integral from 1 to, let's say, b. Now, depending what book you look at, what video you watch, sometimes they use different variables here. B is pretty common. You can really use anything. I'm going to keep my integrand the same, and I'm going to let, where's my thing? I'm going to let b go to infinity. So this is a sneaky way around the issue of having infinity as one of our limits of integration. We're going to say, all right, let's say instead that we're going to go from 1 to b. We'll stop right here. We'll do that limit, or we'll do that integral, but then we're going to send b all the way to infinity. We'll do the limit thing at the very end. Make sure you write this down. The limit comes at the very end after you have found the antiderivative of this and after you have plugged in b and 1 and subtracted. Limits come at the very, very end. That's a big mistake. People do it too soon. So you're still going to do the antideriv. We're still going from 1 to b. We're kicking b all the way to infinity and seeing what happens. So let's just go ahead and find this antiderivative. This limit is hanging out, waiting for his turn. Antiderivative of 1 over x is natural log of x. We should probably use those absolute value bar signs. So I'm going from 1 to b. I'm doing the first fundamental theorem of calculus here. So I'm going to do the natural log of b minus the natural log of 1. It's still the limit as b goes to infinity of this whole thing. Well, natural log of 1 is 0. That doesn't exist. So, or it's 0, I'm sorry. So now I have the limit as b goes to infinity of the natural log of b. The last step of an improper integral is often the most tricky, because you have to, in your head now, find what this is going to be if b were infinity. So picture natural log, the graph. It looks something like this. And think, all right, if b was a larger and larger and larger number, what would happen? So natural log is a very slow growth. But if b were actually to go to infinity, this would very, very slowly keep increasing forever, forever, forever. So the limit would be infinity. It's slow, but it does go to infinity. So because this limit is infinite, it doesn't exist. So we can say that the area is infinite. So make sure you write that down. So again, the main conclusions we're making is because the limit doesn't exist, the limit was infinity, the area is infinite. So if you look at this graph, this area, we can't put an exact value to it. It's going to keep going forever, 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 and therefore the integral diverges. Now let's take a look at another example, which is going to seem very similar, but is actually quite different in the end. Instead of doing 1 over x, let's look at the graph 1 over x squared. Now if you zoom out and look at the whole thing, 1 over x squared has the same vertical and horizontal asymptotes as 1 over x did, except that it's all above the x-axis. So we're going to zoom in on the part from 1 all the way to infinity. Now you might be looking at this and thinking, well, this looks exactly the same as the last one. And it kind of does. So we're going to go from 1, the area under the curve, all the way to infinity, forever, forever, forever. And the only difference is that 1 over x squared actually decreases a little bit faster than 1 over x. And that's going to make all the difference in the world here. Make a note to yourself here because, again, the fact that 1 over x squared goes to 0 much quicker than 1 over x did, that's going to make the difference between divergence and convergence. So let's go ahead and rewrite this as a limit from 1 to b. So I'm going to say, all right, let's say this is b right here. And I'll find the area from 1 to b, but then I'm going to send b to infinity. So then I'll take the limit as b gets larger and larger and larger, which is what we really want. So I'm still ignoring the limit. It's on the outside. And I'm going to go ahead and do the antiderivative of this and plug in. What I did here is I rewrote it as x to the -2 power. I did my antiderivative. The limit is still on the outside. I've done the first fundamental theorem of calculus. I've plugged in 1 and b. Be very careful of this sign change. Minus a -1/1 is +1. Now the hardest part here is thinking at the very end. Let me actually get rid of this here so we can think about this. I'm left with this right here. And now you have to think, if I were to let b to go to infinity now, I'm ready for the limit. If I were to let this get larger and larger and larger, what would happen if I have -1 divided by an increasingly large number? This is going to tend to 0. So this whole thing is gone. There's nothing to plug in here. It's just 1. So this limit is actually 1. The limit exists. The few things we can say here are that the limit exists, the integral converges, and the area under the curve is finite and is 1. So again, notice if I had 1/x, this area was infinite. It was an unbounded integral. If I just kick that degree in the denominator up 1 to be x squared, now this function decreases fast enough as x goes to infinity that this area is going to be bounded, and I can say the total area is 1 under the curve. Now that we've looked at the general rule of 1/x and 1/x squared, the next question is what would happen for different powers of x? So like if I had 1/x cubed, 1/x to the 4th, etc. If it keeps going higher and higher, or if I had something like 1/x to the 1/3 from 1 to the infinity, anything like that. And mathematicians call these types p integrals. Because what we're going to say is, all right, more generally, instead of just thinking of every single possibility, let's call it 1/x to the p. So the question is, when does a limit exist? When does it not exist? When does the integral converge or diverge? What you need to remember is what happens for rational functions. If I have 1/x versus 1/x squared versus 1/x cubed, as the power gets higher and higher, the function decreases more rapidly and gets closer to the x-axis at a faster rate. The opposite is true if I had something like 1/x to the 1/2 or 1 over the square root of x. That is going to decrease at a less quick rate. So if I had 1/x to the 1/3, it'd be even further away from the x-axis. So we're going to say 1/x to the p is the general function that we're looking at. So we're going to say the power function 1/x to the p or x to the -p. Mathematicians call this a p integral. So we already noted as p gets larger and larger, the function decreases more rapidly. The opposite happens if the power gets closer to 0. So it's approaching 0 at a faster rate. The theorem right here states what the rule is. It tells you when the p integral will converge and when the p integral will diverge. Notice p equals 1, which is what we did right here. That is the dividing line between the two cases. So the theorem says if I have 1/x to the p, it's going to converge if my exponent in the denominator is larger than 1. So 1/x squared, 1/x to the 6th, etc. If p is less than or equal to 1, so here p is equal to 1. I have a little exponent of 1 there. Or if it's anything less than that, then the limit will not exist. The area is infinite and the integral will diverge. So in the next the next video, we'll do some more examples. Make sure you have all this information and the whole introduction written down, and we're going to get to some more involved examples.